section 15.8, triple integrals in spherical coordinates. The spherical coordinates system represents points in 3D using three variables: rho, theta, phi. Rho is the distance from the origin to the point xyz. By using the Pythagorean theorem, you can find it easily. Rho is square root of x squared plus y squared plus z squared. Theta is the angle from the positive x-axis to the projection of the point onto the xy plane. And phi is the angle from the North Pole to this line segment, so that is phi. By observing the definition, we can see easily the following. Rho must be non-negative, and theta can be from 0 to 2 pi, 0 to 2 pi whole circulation horizontally, and phi must be between 0 and pi, and is in North Pole, there is 0, and go down to the South Pole, then the angle must be pi. Now, we'll try to get a conversion formula between rectangular coordinates and the spherical coordinates. For a convenient conversion formula, you may consider first these equations. Z is rho sine phi. From the figure, you can easily see that z, the vertical component, can be found here. That one can be found rho now cosine phi. So you can get this one. And also, these ones are as in the polar coordinate. Again, this is again r. So here r is rho sine phi. There's rho and sine phi. So r is a kind of intermediate variable. Now, so from the figure, we can easily see that one. But from polar coordinates, we know that x is r cosine theta, y is r sine theta. So we'll use these two equations to get a convenient conversion formula. Okay, here we have conversion formulas between the spherical coordinates and the rectangular coordinates. Okay, now from spherical coordinates to r, the rectangular coordinates, and we have that x is r cosine theta, and r is now rho sine phi, so that this r is replaced by rho sine phi. Now y is r sine theta, and r is replaced again by rho sine phi. And already we know that z is rho cosine phi. So that is the conversion formula. From rectangular to spherical coordinates, and we may solve these equations to get your first rho and phi and theta. Okay, rho, that is coming from Pythagorean theorem. And then from this one, cosine phi is z over rho. If you find rho, you can get this quantity, so you can decide the phi. And from the first equation, now once rho and phi are decided, then you may divide this term both sides so that you can get that one. Cosine theta is x over rho sine phi. So by solving this equation, you can get phi. That's the conversion formulas. Okay. Plot the points with the spherical coordinates. Okay. Let's try to plot the point and find the rectangular coordinates. Okay. For part A, and we start with the coordinate system. Okay, there's x direction, there's y direction, there's z direction. Okay. Now there's first one is rho, is a length 2, and now there's a pi over 4 in from the positive axis. It is rotating pi over 4, and now from North Pole the angle is pi over 3. So it looks like around here, and length is 2, and the angle from the North Pole is now pi over 3. And if it is projected onto xy plane, then angle from this positive x-axis must be pi over 4. Right? Okay, so that's the point in xy z coordinate. Okay, so we can find the rectangular coordinates. Okay, let's write the formula again. X is now rho. In fact, this r cosine theta, but r is rho sine phi. So we may consider r as an intermediate variable and try to use it here. And this is cosine theta. And y is r sine theta. R is again rho sine phi and sine theta. And z is now rho cosine phi. Right? So from here, you can get easily x, y, z. Okay. Now x is, rho is already here 2, and sine and phi is pi over 3, and cosine theta, cosine pi over 4. Okay, you can get quite easily that one. That is 2, and sine 5 over 3 is square root of 3 over 2. Right? Cosine pi over 4 is 1 over square root of 2. You can simplify this one easily. In fact, that one is same as square root of 3 over square root of 2. Okay. Now y is, and the same here, 2 times sine pi over 3, and then now sine pi over 4. But the quantity is the same, so that again, this whole thing is square root of 3 over square root of 2. And how about z? Z is now rho cosine phi, 2 times cosine, and phi is pi over 3. Cosine pi over 3 is half, so that z must be 1. Right? Now let's go to part B. Find the spherical coordinates of the point with rectangular coordinates. Once point is given in these rectangular coordinates, then we can find the spherical coordinates. Okay. Rho is now square root of x squared plus y squared plus z squared. So that's 0 plus that is 12 plus 4. So that rho is 4. Right? Now cosine phi, okay, cosine phi from this one, you can get it. That is z over rho. Okay, what is z? Z is minus 2 over 4. That's minus half. So from here, now phi must be 2 pi over 3. Then cosine phi is minus 1/2. Okay. Now, finally, you can get theta, cosine theta, by using this first equation. Now, that is same as x over rho sine phi. What is x? X is 0. So no matter what it is here, it doesn't matter. That is 0, right? And x is just the x is 0. So that is 0, which means that theta must be pi over 2. So we have, and 4, that is the first component, that is the second component, and the third one, right? Now, this spherical coordinates system will be used for integration, triple integral. And once here spherical wedge is given, and in this way, rho theta phi, rho is from A to B, theta is from alpha to beta, and phi is from C to D. So some expansion of this one will be the spherical edge. And from this one, once we try to partition in every direction, in rho direction, theta direction, and phi direction, then this will be a spherical wedge. Let's try to find the volume of this spherical wedge. Okay, here, and this one, that distance is change in rho, so delta rho. And when we consider arc length in a sector, we already found that this is r, the radius r, and then because we consider your horizontal direction, there's r and angle change, that horizontal angle change, that's delta theta. And again, same. Now, yes, with this vertical change, that is rho and delta phi. So that is the length. So we may consider this one as a rectangular box, and the area, the volume, can be approximated by just these three multiplications. In fact, you have to do a little bit better, but eventually we'll reach at the same result. So we try to multiply here three length in delta rho, and r delta theta, and rho delta phi. So we have that, and we can rewrite in this way, and r and rho, but r is already, we know, is rho sine phi. We considered this one as an intermediate variable. R is rho sine phi. Okay, and eventually the volume for the ijkth spherical wedge, we have this formula: rho squared sine phi, delta rho, delta theta, and delta phi. So it is the scaling factor between rectangular coordinates and spherical coordinates. Okay. So we have this formula for triple integral on spherical wedges. E is a spherical wedge, so the rho is from between A and B, and theta is between alpha and beta, and rho phi is between C and D. Then this triple integral can be written in this way. So it looks like this is integration over box, and the same f expressed as a function of rho theta phi, and scaling factor is rho squared sine phi, and that integration is over rho theta phi. And we'll try to keep this order only in the spherical coordinate system. Anyway, here the scaling factor is rho squared sine phi. That is the same as rho and r multiplication. Okay, now we'll try to solve some problems. Evaluate triple integral over b of that function, and b is the unipole. Okay, once we are considering unipole, then if we try to visualize it, there's like this one, xyz coordinates, and then unipole, and of here radius 1 is given in this way. Okay, now then now the given integral can be written. Now outmost integral is phi integration. Phi is from north pole to south pole, so it is from 0 to pi. How about horizontal rotation from x-axis? Now its rotation is whole rotation, so that from 0 to 2 pi. And how about rho? Rho is now from 0 to 1, so we have that. Now there's e to the, this itself is rho squared, and power 3 over 2 makes rho cubed, right? Okay, just a moment. I wrote down only in 3, so that e to the rho cubed. Okay. Now the scaling factor, you should not forget scaling factor, that is rho squared and sine phi, and then the integration order is the rho, the theta, the phi, right? That is the scaling factor, and this is order of integration. This is a separable, that is a box, so that you can get the solution separately integrating the each part. Okay. For phi integration, we have a sine phi, so that from 0 to pi, that is sine phi and d phi. For theta integration, we don't have any theta component, so the immediately we can get here, that is 2 pi. Okay, and then finally rho integration from 0 to 1, now rho squared and e to the rho cubed and d rho, right? Okay, for this first one, the integration antiderivative is minus sine phi in 0 pi evaluation, then you will get here the value 2. The second one is 2 pi, and the final one is antiderivative must be some coefficients times e to the rho cubed. And once you try to get derivative of that one, then there will be this one times 3 rho cubed, so that 3 will appear extra. So we have to put here 1/3 to match the equality. Okay, so we have that, and evaluation from 0 to 1. So these coefficients makes 4 pi over 3, and once rho is 1, then E, and rho is 0, then that is now 1. Right? So we have this final answer. 4 pi over 3 times E minus 1. Okay? Now for more general regions, and we can also use Fubini theorem, so we call it spherical Fubini theorem. We can extend the theorem to regions defined by, in this way, rho theta phi. Now here rho, that is basically innermost integral, is now bottom and top are functions of theta and rho, that is innermost variable. And for theta and phi, these are just a rectangle in a sense. Then we can get this integral. That is now the triple integral over E can be written in this way. So first we have rho integration, this bottom rho and top rho as functions of theta and phi. After getting that one, you can make a theta integration and finally phi integration. So a little bit more general spherical coordinate domains, you can get iterated integral. That is the idea of this theorem. Okay, yeah. Let's try to solve this problem. Use spherical coordinates to find the volume of solid that lies above the cone. Z is square root of x squared plus y squared. And so in fact, once we consider R component, that is the same as R anyway. And below the sphere, x squared, y squared, z squared summation is Z. Okay, for that one, you can write in this way. Z is moved here, then z squared minus z, so it can be written in this way, x squared plus y squared, and plus z squared minus z can be written z minus 1/2 squared. Then 1/4 is added, so we write down on the right side 1/4, like that. So it can be written in this way. That means this one, sphere, is, okay, this is upper portion of the sphere. Now, that is center. The center is x in 0, y equals 0, and in z direction, center is half. And for that one here, the radius, okay, let's say, we'll try to say r is half. So that sphere, the whole sphere will touch the xy plane, and it's made in this way. Okay, so we have to recognize the shape of given objects anyway. Now, to get the volume, okay, we have to use spherical coordinates. First of all, now that one, this equation, we can express it this way, or now that is rho squared is z is rho cosine phi. So we can reach at that one. In fact, rho is, okay, for every point inside, rho is coming from 0 to the point over there. So that this is a final rho. And once you are trying to access the region and from 0 to the end of that end point is now rho is cosine phi, right? Now phi is angle from top to this one, and this angle can be decided from this one. Z equal R means that now the angle, the maximum possible angle from the North Pole must be pi over 4. So in that direction, so final angle must be pi over 4. And how about horizontal direction? In horizontal direction, and we can make whole circulation so that theta must be from 0 to 2 pi. So the volume can be decided by using this equation. Now theta, no, it's phi from 0 to pi over 4, we found here, and theta whole circulation from 0 to 2 pi, and rho is from 0 to the end, the maximum rho is cosine phi, right? So we access the domain in this way, and original integrand is 1 because we try to find the volume, and this one is a scaling factor, and integration order is rho theta phi, right? Okay. Now from here, that one, okay, from this one we try to make in the beginning here rho integration, but theta direction is independent, so that we can finish this one first, just theta independent. And so that we write down this one in this way. We're done. Now theta integration, and remaining part is here, that one, phi integration from 0 to pi over 4, and we'll try to finish this portion, rho integration, that is, and sine phi is a constant in rho integration, and rho squared will be 1/3 of rho cubed, and then rho is from 0 to cosine phi, right? After getting this one, we'll try to get the integral over phi. Okay. Okay, we'll rewrite this one, and 1/3 will go out, so there's 2 pi over 3, and integral from 0 to pi over 4, and this whole thing is now cosine phi cubed. So the sine phi times cosine cubed phi, and 1/3 went out, and now d phi, right? Okay, from this one, 2 pi over 3, and that one, the antiderivative must be with some quotient, and there must be cosine 4th power of phi, right? And 0 to pi over 4. Okay. And we have to decide this quotient. Okay, in order to do that, let's try to differentiate this one. Then there's 4 will come out, and cosine cubed theta, and times minus and sine theta, right? So to match each other, we need here this minus 4 divided by minus 4, so that 1 over minus 4 must be here. Then now we are okay. Okay, so by combining these two, we have now that is a 6 and 2 pi on the top, right? And here, along with this negation, we first evaluate with theta 0, which is 1, and theta is pi over 4, then 1 over square root of 1 over square root of 2 is fourth power will be 1 over 4. Okay, if you simplify this one, and then, okay, the answer must be pi over 8. So that's the final answer. Okay? Okay, that's the end of section. Thank you.